Ceramics are hard and brittle materials. The brick in the figure is made of ceramics. The properties like stiffness and strength can be very good for structural applications, but the lack of ductility usually prevents this. Good properties for ceramics are the temperature resistance. They can be used at a very high temperature. Another useful property is the wear resistance of ceramics. Therefore, these materials are often applied in cutting tools. The accident with Space Shuttle Columbia in 2003 illustrates the brittleness of ceramic materials. 7 persons were killed in that accident. The probable sequence of events was that during takeoff a frozen block of foam hit the leading edge of the shuttle and made a hole in it. The leading edge is made of a ceramic named carbon-carbon composite. The ceramic has high temperature resistance and should act as a thermal protection system for the aluminum structure inside the shuttle. The foam made a hole in that leading edge, allowing hot air gases enter the structure. During re-entry of the vehicle, those hot air gases destroyed the shuttle, and that was recorded live on television. An extensive research after the accident involved testing to simulate the events. Therefore, a leading edge section of the same ceramic material was mounted on a rig and impacted by blocks of foam. It appeared that the edge could be damaged, resulting in the awful scenario described before. The last group of materials is composites. Fiber-reinforced polymers are fibers embedded in a polymer matrix. Fibers are the strong and stiff component, so the material is stiff and strong in fiber directions only. This may make the fiber-reinforced polymers highly anisotropic, which can be exploited. If, for example, a profile is loaded in length direction, the majority of the fibers should run in length direction. Only a minor part is needed in transfer direction for the sake of coherence. Preforms, where all fibers are oriented in one direction, are named unidirectional. To create cross-ply laminates, we can place UD preforms in 2 orthogonal directions. Composite laminates consist of multiple layers, or lamina, stacked together and consolidated in a separate pressure-temperature cycle. Fiber-reinforced polymers have 2 distinct ingredients, each with its own specific functions. The fibers provide the strength and stiffness, and the polymer is the matrix in which the fibers are embedded. The functions of this matrix are providing load transfer from one fiber to the other, support of fibers in case of compressive loads, and protection of the fibers. When a stress-strain curve is constructed for a composite, you can see that the composite curve is a mixture of the curve of fibers and of polymers. Polymers do have some plastic deformation capacity. Fibers not. They are elastic until failure. Besides, the failure strain of fibers is very small, 1 to 4% for most common fibers. The properties of fiber-reinforced polymers are its high specific strength and stiffness. This is also the result of the low density of composites, between 1.4 and 1.8. A disadvantage is the low failure strain or the lack of ductility. A special feature of composites is its anisotropic behavior. This can be used to reduce the structural weight even further. For example, the stringers in the fuselage section of the Boeing 787 in the picture have most fibers, about 50 to 60%, running in length direction. For the fuselage skin, the panels can be placed in hoop and longitudinal direction in a ratio of 2 to 1, according to the stresses resulting from the cabin pressure. The last slide shows a hybrid material, a combination between metal sheets and a fiber-reinforced polymer. In this case, the polymer matrix is also the adhesive to bond the separate layers. The glare material has been developed at the aerospace faculty of the TU Delft as a dedicated fatigue-resistant material. Its properties, represented in a stress-strain curve, is a mix of the properties of the ingredients. Metal sheets provide ductility, are isotropic, and have high strength and stiffness values. The fibers provide extra strength and stiffness, fatigue resistance, and high energy absorption during impact. And finally, the polymer or matrix is supportive and protective and bonds the ingredients together.